So we introduced this idea of the formula weight, the balanced chemical formula, and how we can use mass information to determine numbers of products or predict how much starting material is needed. And so very flexible. But there's other information buried in the chemical formula that might not be 100% obvious. One of the bits of information that's buried in that formula is the ability to figure out what we call the percent composition, or the mass percentages of elements within a compound. The reason this is useful is because a pure element, a compound that's pure has a fixed ratio of atoms, usually a small whole number. This is something that, again, goes back to Dalton's. That means that if the compound is pure, the mass percentage of each of those elements will always be the same. So let's take a look at P4O10. If we look at that,
there are 4 moles of P in 1 mole of that compound.
10 moles of oxygen, and we can use the periodic table to figure out the total mass of all of the oxygen and all of the phosphorus. 123.892 grams of phosphorus present in those 4 moles, and 159.9994 grams of oxygen present. Again, this is information right from the chemical formula. We can then find out the percent oxygen and the percent phosphorus simply by dividing the total mass of the oxygen divided by the mass total times 100 to give us our percentage. Or in this case, we can find that this would be equivalent to 159.994 grams of oxygen divided by 283.88 grams total times 100 to give us the percent of oxygen, which in this case would be 56.4%. And we could do a similar calculation with the phosphorus and find that it'd be 43.6%. Now what's cool, I guess, is that regardless of the source of P4O10, there will always be 43.6% phosphorus by mass and 56.4% oxygen by mass. Notice how different this is from the mole ratio. P4O10, there's more than twice as much oxygen by mole than there is phosphorus. Yet, the mass ratios are very similar. They're almost 1-to-1. So we can find the percent composition of almost anything, if we know the formula. But here's something cool. You can use the percent composition to figure out the formula. So we can go from the formula to the mass percentages very easily. But we can also use the mass percent to calculate a formula. Now this formula may not actually be the molecular formula. It may be what we call the empirical formula. The empirical formula, as the name implies, empirically derived, is usually derived from real-world data. The empirical formula is the simplest whole number ratio of atoms. For instance, H2O2, there's a simpler ratio that would describe the relationships between the hydrogen and the oxygen. The least common denominator in this case, 1-to-1. Something like many sugars, C6H12O6, the empirical formula would be H2O. Is a reduction of all of the formula to the simplest whole number ratio. What happens is that many compounds share empirical formulas. If we look at mass composition data, it can never tell us anything more than the empirical formula. We can't necessarily see from the empirical formula whether or not there is a higher order to the formula. And for that, we have to turn to other information. So let's take a look at an example. Let's see if we can use mass information to figure out a formula, an empirical formula. And the way we usually do this is, well, what did we do before? How do we go from formula to mass percent? We took the moles and converted into grams, and from that we could convert that into a percentage. Well, let's just reverse the procedure. Take our percentage, convert it into grams, which I've done in this case. Just as a quick tip, you know, if something is 77.7%, we could just pretend that we have 100 grams of total. 7.77 grams. So you can then convert that into something. So percentage to grams is easy. You just assume you have 100 grams. So once we have our mass, we can then convert that into moles. So let's take a look at an example. We have a compound that contains just lithium and nitrogen. They don't tell us that it contains anything else. That's good. It contains just lithium and nitrogen. We can use the atomic mass of lithium to figure out how many moles of lithium. This is a simple gram to mole conversion. We know that 6.941 grams of lithium is equivalent to 1 mole of lithium. Of lithium, leaving us with 0.861 moles of lithium. Then we can do the exact same calculation with the nitrogen, and from the formula it gives us 0.287 moles of nitrogen. Now, this doesn't look like a small whole number ratio, which it isn't a small whole number ratio unless we actually make it into a ratio. We divide the lithium by the nitrogen, we divide the largest by the smallest, and that'll give us the whole number ratio. Because whenever you do a division, whenever you take a ratio, well, that sets the bottom to 1. That sets the denominator to 1. So if we take 0.861 moles of lithium and we divide it by 0.287 moles of nitrogen, that sets this lithium to nitrogen ratio. The nitrogen would be 1, is 2.99, which looks surprisingly like 3 to 1. So that would be 3 lithiums for every 1 nitrogen, which would give us a formula, Li3N, which is exactly what we expect for the chemical formula for the compound formed between lithium and nitrogen. And if Dan was being particularly mean, we would name this lithium nitride. Favorite question on a test. Using the percent or mass information, determine the empirical formula. Now, if you know the empirical formula, you know its mass. Again, it's just simple. And if you know the molecular formula, you know its mass. If those two numbers are not the same, they will likely be whole number ratios. And so if you know the molecular weight of a compound, which you can actually determine via other methods, you can just take the molecular weight and divide it by the empirical formula, and that gives you a scaling factor. So if the empirical formula mass was 10 and the molecular formula was 20, you'd know that you would have to multiply the empirical formula by a factor of 2 to get to the molecular formula. That's the easy way of determining empirical formulas. It's probably a hard way. It turns out that conventional element analysis is actually quite common. Elemental analysis is one of the ways we as chemists use to prove that our compound is pure. Pure compound will have a fixed ratio, so if I predict that the compound has this particular formula, and I go and analyze it, the mass percentage of those formulas should match my calculated values. Now, how do we actually do this? Usually, we have some carbon and hydrogen containing compounds, maybe some oxygen in there, and you burn it literally in oxygen, which creates the CO2 and water from our previous examples. Now, in this case, all of the carbon comes from that compound. And so you use specialized capturing material to suck up the CO2, and you can weigh the CO2 that's generated, and you can weigh the water that's generated. We know from the formula that one water molecule is equivalent to 2 hydrogen atoms. So we know how many moles of carbon, we know how many moles of hydrogen, and from that we can figure out the empirical formula. So in practice, we weigh the CO2 and we weigh the water, and then we go backwards. One of the problems, though, is that oftentimes, if there's oxygen or some other element present, it also ends up as a product, and we don't necessarily capture that. But if we know the total mass, we can subtract out the mass of the carbon and the mass of the hydrogen, and if it equals 0, it means that there's nothing but carbon and hydrogen. If it doesn't equal 0, it means that the leftovers are the oxygen or other element. So it's kind of a nice trick, right? We don't often think about it, but if we know how much we start with and we know how much we end up with, whatever's missing is the other elements present. Okay. So how do we go about this? Again, elemental analysis, determine the moles of each element. That's pretty simple. Take your grams of whatever carbon and convert it into moles of carbon. Once you have the moles of carbon, the moles of hydrogen, and the moles of whatever else, you divide them by the smallest. So if it was moles of hydrogen, this would set this to 1, or this would set this H to carbon ratio. And then we check the formula for validity, make sure it's valid, no halves, no fractions. Occasionally you'll get a number like 1.5 or 0.333. Don't round. Right? What this represents is half an atom, which we can't have. So it might represent a ratio of like 2 to 3. And that would give you a value like that. So let's take a look at a problem. You have a sample, total mass of the sample was 5 grams, and it's found to contain the following: 0.227 grams of hydrogen, 1.622 grams of carbon, and 0.9456 grams of nitrogen. Now, just by looking at that, you can see that looks like there's some oxygen missing. How much oxygen? Well, so the total mass was 2.8398 grams. That means that the remaining mass, 2.1602 grams, was oxygen. Once we know that, though, it's pretty trivial just to convert each of these values into their respective number of moles. I'll let you do that. So you get down to the end, and you see that from your mole percentages that the nitrogen is present in the smallest amount. So if we take the moles of hydrogen and we divide it by the moles of nitrogen, that'll give us the hydrogen to nitrogen ratio. So this hydrogen-nitrogen ratio, first step, convert grams into moles. Next, take the mole ratio. Once we have the mole ratio, it says that there are 4 hydrogen for every 1 nitrogen. That's what the mole ratio is. Then we can do a similar analysis for the carbon. It says that there are 2 carbon for every 1 nitrogen, 2 oxygen for every 1 nitrogen. And let's 2 oxygen for every 1 nitrogen. And let's not forget the nitrogen, 1 nitrogen. So the formula, the empirical formula for this compound would be C2H4NO. 2. That's empirical formula in a nutshell. We'll do one harder one in the class that involves combustion analysis, what we just talked about. We have grams of a material and we convert it into CO2 and water. This is a good practice problem. Let's try this one out.